All right, confession number 2. So this one is actually pretty humiliating. It's a pretty glaring mistake, but in this video I talk about composition and speak in terms of felsic and mafic, and this will all make way more sense as you watch the video. But what I say in the video is that felsic igneous rocks have more silicate minerals than mafic igneous rocks. And this is fundamentally incorrect. Every time I say that, what I should have said is that felsic igneous rocks have more silica within the silicate minerals than mafic rocks. I.e., both felsic and mafic rocks have silicate minerals. There's just more silica within felsic rocks. And this will make a lot more sense as you watch the video, and I'll try to add some animations to clarify and point out when I just totally screw it up. But there's that. Hopefully that helps, and I hope you enjoy the video otherwise. Okay. Be back. All right, so that brings us to composition. What? But Ethan, what if we see a rock with mostly small or indiscernible crystals with a few larger crystals mixed in? That's a great question. Love that question. You're probably seeing a rock that is actually both intrusive and extrusive, or rather spent the first bit of its life as a body of magma where it was cooling minerals slowly in the subsurface, right? Before it decided it'd rather be a lava. And skadoosh, it erupted and finished cooling at the surface, wherein those intrusively cooled crystals became suspended in an extrusively cooled matrix. And we actually call that type of texture porphyritic. And this is a great example of a porphyritic igneous rock, right? This andesite here, you can see, has a bunch of larger crystals that you can clearly see suspended in this grayish matrix that is extrusive. That's awesome. I love that question. That's a great question. All right, so now we know that crystal size tells us about texture, and texture tells us whether an igneous rock cooled intrusively or extrusively. But that's only the first half of identifying igneous rocks. Now let's talk about the second half, which is composition. Recall from the sedimentary rocks video that when we talk about composition, we're actually talking about the chemical makeup or the mineralogy of that rock. And usually, as soon as I say chemical composition or mention chemistry at all, students are like, nah, I'm out, not dealing with that. But before you turn this video off, you should know that igneous rocks actually make it a lot easier than you might expect to understand. So stick with me, just hang in there. If you think back to the minerals video, yes, the minerals video, I talked a lot about silicate minerals. Then I talked about them again in the sedimentary rocks video. And that's because these suckers are actually really important. In fact, they're so important that they're the second big identifier for igneous rocks. That is, we use the relative proportion of silicate minerals in any given igneous rock to help identify that rock. So how in the heck are we supposed to tell how much of a rock is made up by silicate minerals? Well, to truly know exact proportions, we need some fancy lab equipment. But when we're out in the field, we can actually make some really educated guesses simply by looking at color. Generally speaking, the lighter the color of the igneous rock, the more silicate minerals it has in it. And then the darker the color, the fewer silicate minerals you can find in there. And so we can think of igneous rocks as having generally two end-member compositions. On one side, we have felsic compositions, which is what we call rocks that have high proportions of silicate minerals. And on the other side, mafic, for rocks that have relatively low proportions of silicate minerals. So we can actually see this if we revisit some of the rocks we've already seen in the field.
Yeah, and as we can clearly see, the basalt here at Silver Falls State Park is dark in color. And what that tells us is it's made up a lot less of silicate minerals and more of things like iron and magnesium. So because it's dark, we know that it's a mafic extrusive igneous rock. Yeah, and this rhyolite is obviously lighter in color than the basalt was, which tells us it has a higher percentage of silicate minerals and is thus a felsic extrusive igneous rock. Yeah, so it can be a little bit trickier with intrusive rocks because the mineral grains are so much better differentiated, of course. But looking at this as a whole, looking at the rock on average, I would say that this rock is mostly light colored, right? Despite being able to see all these these dark minerals, we say that this is mostly light, and so this is in fact a felsic rock. And in fact, granite by definition is felsic, so we know that this is felsic. Though, if I hadn't mentioned earlier that this is granite, so you didn't know it was granite, you could come up to this rock and say, well, it's mostly light, so I think it's felsic in composition, and I clearly see different mineral grains, so I know it's intrusive. So now I'm thinking about an intrusive, felsic, igneous rock. Well, granite's a pretty dang good option there, and in fact, you would be right in calling this granite. And that's how we start to identify igneous rocks. Pretty cool, huh? So there's actually one more composition that I want to talk about beyond mafic and felsic, but I think it'd be best to do that back in the classroom. So let's pop back there.
Oh gosh, that was not as smooth as before. Okay. Wait. Composition. Right. So if we get back to our compositional spectrum from felsic to mafic, right? There's actually a third composition which we call ultramafic, which is beyond mafic, obviously. And these rocks are actually a lot rarer at Earth's surface and are typically really dark green due to minerals like olivine and peridotite, which are abundant in the mantle, where ultramafic rocks are more likely. All right, I don't really want to say too much about ultramafic, but it's good to know about. Moving on. Maybe not. What do we got here? But Ethan, what if we see a rock that's really hard to determine if it's light or dark? What if it's right in between? That's another great question. I love it. Yes, if a rock is neither clearly light or dark, like these rocks in the middle here. Obviously, we've got some light granite over here and rhyolite and some dark mafic basalt over here. But if it's hard to tell, we very creatively call that an intermediate composition. Yes, very creative. But that just says that parent magma to this didn't have abundant amounts of silicate minerals, but it wasn't necessarily silicate poor either. It was of an intermediate composition. Great question. So that's actually a perfect question because it leads us to the next major point, which is that the composition of igneous rocks is dependent on the composition of their parent magmas. It's important to know that not all magmas are created equal. And if you think about this, the fact that magmas can have different chemical compositions is actually pretty weird, right? If all magma is the product of the mantle, how is it then we can have magmas creating such a wide variety of igneous rocks? To understand this, we have to understand the ideas of fractional crystallization and Bowen's reaction series. And as much as I love teaching about these things, I thought I'd ask my friend Emily, who specializes in this sort of thing and is way smarter than me, to pop in and help us understand them. So let me make some room for Emily here. Yeah.
Oh wow, you really meant during lunch.
Yeah, I did. Are you still okay to chat about igneous rocks and composition and stuff?
Yeah, I love igneous rocks.
Awesome.
Where are y'all at?
So I'm hoping we can talk about Bowen's reaction series, fractional crystallization, and just kind of moving into understanding how, if magma's all coming from the same place, the mantle, how we can get so many types of cool igneous rocks from magma.
Awesome. So the minerals that actually form an igneous rock form in a particular order, which we call Bowen's reaction series. Right. So let's take a closer look at some of our friends from the minerals lab. Now, this can be an intimidating looking graph, but it helps me to think of the middle two arrows like a ladder and an escalator, with different igneous minerals forming at each new step. On the far left, we have temperature. Our lava is fully molten at the bottom, and the very first mineral to form on this ladder arrow is olivine. As the lava cools, more and more silica-rich minerals form. The arrow on the right is a little more like an escalator than a ladder. It's all plagioclase all the time, but we're just changing up what the composition of that plage looks like. It's calcium dominated when it first forms, and then when all the calcium is taken up, sodium starts dominating the chemical composition. So when we're reading this chart from bottom to top, or hot to cold, we're thinking about what geologists call fractional crystallization, or the order in which minerals form as a system cools down. Depending on what elements we start out with in our system, we might not get a rock with all of these minerals every single time. So let's think a little bit more about those ingredients. Perfect. So we can't get something from nothing. Right. So the magma that we see at Earth's surface has to come from somewhere. That somewhere is often the mantle, which, if we remember, is itself a very hot rock. So thanks to plate tectonics, heat from the mantle can also interact with pre-existing rocks, like the oceanic crust, which is mafic, or the continental crust, which is more felsic, at places like mid-ocean ridges, ocean island arcs, and continental arcs. So whenever we create a melt from a pre-existing rock, whether that's the mantle or some other crust, we think of this as partial melting. So to discuss this, we have to turn the temperature arrow on Bowen's series around and think about what happens if we heat up rocks rather than cool them down.
Right.
If we're melting a rock, then the most silica-rich minerals, the ones that cooled or formed last, are going to be the very first thing that we lose. After we lose all of those minerals, we'll start to lose the next most silica-rich ones, and so on. Actually, my lunch has a pretty great way for us to think about this.
Yeah.
So,
Do you need to?
yeah.
Okay.
So imagine that this trail mix is an igneous rock. So when we partially melt this rock, we're not just grabbing a handful like this. We're taking out one ingredient first. So what's the easiest thing to eat?
M&Ms.
Yeah,
Yep.
right. So imagine that our M&Ms are a silica-rich mineral like quartz or feldspar. And this dried fruit here is a more intermediate mineral like pyroxene or, a sodic feldspar. And then these nuts, which are the last thing that we'd want to eat, obviously, are our mafic olivine. So if we take out all the M&Ms and then we cool down the systems again, we have two rocks, right? One is a lot more silica-rich than the other. So we have a more felsic or intermediate rock, and then our initial rock is more mafic or even ultramafic. And so this means that when we melt a basalt, which is a mafic rock, we can create a more felsic rock, like an intermediate andesite or a felsic granite or rhyolite.
Right.
So if we repeat this process enough, melting and melting a mafic or ultramafic rock, which is what the mantle is, then we can end up with a lot of felsic rock, which is what our continental crust is. So this is a pretty simple way of thinking about how we've gotten the continental crust here on Earth. We've been partially melting the mantle for 4.5 billion years.
Yeah, it turns out that's quite a bit of time.
It's a lot of M&Ms.
Yeah, it's a lot of M&Ms. So this helps us understand why we find different types of igneous rocks at different tectonic settings, right?
Yeah, exactly. So if we have something that's mafic or ultramafic, like the mantle, and we're repeatedly melting that, we're still going to end up with a pretty mafic rock. So we think about seeing that at like a mid-ocean ridge, right? And that's how we get a lot of basalt. But if that heat from the mantle is interacting with a more intermediate rock, like our continental crust, which is mostly, generally andesitic, then we are going to be extracting something that's even more felsic. Right. So that explains why we might see rhyolites, which are really high in silica content, at like our continental arcs.
Right. That makes sense. Man, this stuff is so cool. I feel like we're just barely scratching the surface here, and it makes me wonder if I made a mistake being a sedimentary geologist.
Well, I have my opinion on that, but I'll keep it to myself.
Yeah, let's keep that to yourself. Well, thank you so much for popping in, and I'm really sorry about interrupting your lunch, but you obviously did a much better job at explaining the stuff than I would have.
Totally fine. We still got to eat some of the trail mix.
This is true. So, is there anything else you wanted to add?
No, I think that about covers it.
Great. Well, in that case, I'll send you back to finish your lunch in peace.
I can just walk down the hall. All right.
You sure? It's fun.
Yeah. See you next week.
Okay. Thank you. All right. Well, I think that covers it. I think we covered everything. So rather than leave you here in a classroom, though, I thought we could go check out one more really cool spot just here in Wisconsin.
Yeah, perfect. Oh, this is beautiful. Okay, so for our last stop here in this Igneous Rocks video, I thought I'd take you just into our backyard. I'm in Montello, Wisconsin, looking at a spectacular igneous rock. And so learning or using what we've learned today, right, we can begin to identify this. Thinking first about its texture. Are these large or fine crystals? Can we see them with our naked eye or not? And what does that tell us about intrusive versus extrusive formation? What about the color? Are we looking at something that's more light colored or dark colored? And what does that tell us about its composition? Felsic, mafic, is it in between? I'm not actually going to give you the answer because that's the whole point, right? You can do that now. I will say though that this is actually a really special rock to the state of Wisconsin, which is a pretty big hint. So if you think you know what kind of rock this is, I'd love to see it in the comments. Regardless, as ever, my goal in all of this is to give you a tool for your tool belt that helps you just appreciate how wondrous this planet is. So, until next time, see ya.